This is Unit 2, Lesson 7, Part 3. We're going to complete our discussion on velocity, position, and acceleration. So example 6 says, complete the table below to find all the possibilities for an object's motion. Remember that an object's velocity is either positive or negative, so moving right or up for positive and left or down for negative, or zero, that means it's stopped. Also that an object's acceleration is either positive, negative, or zero, which means you have constant speed when it's zero. Okay, so when the velocity is greater than zero, we have that the particle is speeding up, make this a little bigger. When the acceleration is greater than zero. When the acceleration is less than zero, the particle is slowing down. And when the acceleration is zero, it's at a constant speed or constant acceleration. Okay, so now when our velocity is less than zero, but our acceleration is positive, it is slowing down, so it slows down because they have opposite signs. When the acceleration and the velocity are both negative, that means the particle is speeding up, so it speeds up. And when the acceleration is zero, again, it is moving in a constant velocity. And in the first case, it would be moving to the right, and in this case, it would be moving to the left. Okay, what if our velocity is zero? So that would mean that it is stopped, and it's accelerating. So if we have a positive acceleration, that means it's going to start moving up or right. So if the particle is stopped, again, but the acceleration is negative, it's going to start moving down or left. And then finally, when the acceleration and the velocity are both zero, the object or particle is at rest. Okay, these are some good things to remember when you're looking at velocity acceleration charts or graphs. Okay, so here's some important terminology that we've been using throughout this section, summarized here. Displacement over an interval A to B is the total change in position from where you ended, subtracting where you started. The average velocity is displacement over the elapsed time. So you take your displacement and you divide that by how much time is elapsed, and of course that is going to give you the slope of the secant line. And your velocity at any time t is the derivative of the position function at that specific point in time. So that is the slope of your tangent line. And remember that speed is the absolute value of velocity. It is always positive, so you can write it any of these ways. The word velocity, the absolute value of the velocity function, or it's also the absolute value of the derivative function. Total distance traveled is the sum of the absolute values of the distances between turning points. So this is a little different than the displacement. And then finally, direction changes. So when the velocity changes from positive to negative or negative to positive, that's a direction change. When the velocity does not need to pass through zero, even to be defined at a point where its sign changes in order for there to be a direction change. You could have a jump, something like that. It doesn't have to be a connected graph. Just want you to make you aware of that. Okay, let's do example 7 now. We have a more typical position function because it is affected by gravity. We've seen a lot of these over the years in math and also in physics if you've taken physics. So we have a model rocket that is launched vertically upward from the ground level with an initial velocity of 114 feet per second. The position of the rocket can be modeled by S of t equals negative 16t squared plus 114t. So we are to find the velocity and speed of the rocket at t equals 5 seconds. So that means that we need the velocity function, which is the derivative of the position function. So if I take the position function's derivative, I get 32t plus 114. So now I want to find the velocity at 5 seconds. So I'm going to substitute 5 into the velocity function. And I get negative 46 feet per second. So the velocity is negative 46 feet per second, and the speed is positive 46 feet per second. Okay, part B. Is the rocket speeding up or slowing down at t equals 5? Explain how you know. So what I want to do is take the derivative of my velocity function, because that'll give me the sign of the acceleration. And we can go back and look at this chart. Since our velocity is negative at this point, we would want that if it's speeding up, we would want our acceleration to be negative. If it is slowing down, we'd want our acceleration to be positive. So we're going to take a look at that. So we're going to find the derivative of the velocity function. So we're going to find v prime of t, which is the same as s double prime of t. So we're going to get negative 32. It's a constant. So this is negative. And v of 5 is negative. We found that in the last part. So it is speeding up. And our justification is going to be the velocity and acceleration have the same sign. Okay, part C, what is the maximum height the rocket will reach? Well, that's going to happen. The maximum height is going to happen when the velocity function equals 0, because it's going to go up, it's going to stop momentarily, and then change directions. So we're going to set the velocity function equal to 0 and solve for t. And when we do that, we get negative 32t equals negative 114, and t is going to equal about 3.5 seconds. So I put this in my calculator. That's the exact answer. So that's that time. So then what I have to do is find the value of the function at that time, my position function, and that comes out to be approximately 203 feet. Okay, what is the speed of the rocket when it hits the ground? So that means we need to know at what time that the rocket hits the ground. So we're going to set the position function equal to 0. So we set negative 16t squared plus 114t equal to 0 and solve for t. So I'm going to factor out a t. And when I solve this, of course, we get t equals 0 before it was launched. And the other time is going to be t equals 114 over 16, which is 57 over 8. And so then I have to find, I want the speed, not the velocity. So I'm going to take the absolute value of the velocity function at 57 over 8 seconds. And when I do that, I'm going to get 114 feet per second. Okay. So then finally, the effect of 1 unit change. So we know that for very small values of h, the approximation of the derivative can be found by the difference quotient. It can be shown that the approximation can be found when h equals 1. That is, h prime at some specific point is approximately equal to f of x0, I'm sorry, I said h prime. F prime of h0 is approximately equal to f of x0 plus 1 minus f of x0. So just to clarify, f prime of x is approximately equal to the change in f caused by 1 unit change in x when you're talking about your specific x value that you're trying to find the change. So we're going to go through and do an example where this is a helpful concept to have. Okay, for speeds between s equals 30 miles per hour and s equals 75 miles per hour, the stopping distance after the brakes are applied for a vehicle can be modeled by the formula f of s equals 1.1s plus 0.05s squared feet for a vehicle traveling at 65 miles per hour. Okay, so in part A, we're supposed to find the actual stopping distance at 65 and 66 miles per hour. And then we want to know what the stopping distance needed for an increase in speed of 1 mile per hour. So what we're going to do is we're just going to evaluate our function. We're going to do f of 65, and we're going to do f of 66. And then we're going to compare those distances. So we're going to do 1.1 times 65 squared plus 0.05. Whoops, I'm sorry. The squared goes with the second term. 0.05 65 squared. And when I do that, I get 282.75 feet. I'm sorry. Yeah, feet. For a second there, I was mistaken. Feet. Okay, and then 1.1 times 66 to find the stopping distance for 66, 0.05 times 66 squared, and this is equal to 290.4 feet. So what is the distance increase? So we just have to find how far apart these are. So we're going to do f of 66 minus f of 65, and so we're just going to subtract these two numbers. And when we do that, we get a change of about exactly 7.65 feet. Okay, then part B says, estimate the change in stopping distance if the speed is increased by 1 mile per hour using the instantaneous rate of change at s equals 65. So that means we want to find the derivative of f of t. So we're finding f prime of t, s. F prime of s is going to equal 1.1 plus 0.10s. And so then f prime of 65 is going to be 1.1 plus 0.10 times 65. So our instantaneous rate of change at 65 comes out to be 7.6 feet. So you can see we're pretty feet per minute. So this is actually, let me get my units right. I'm so sorry. Per mile per hour. So these two are very close. Very, very close. So you can see that 1 unit of change is a useful concept, especially if you have a function and it's difficult to take the derivative. So we're supposed to compare the estimates now in part C. So what we want to see is how close is f prime of 65? Is that relatively close to what we found in part A? That's what we're trying to see. If this change is pretty close. And what we find is that it is almost exactly the same.